Hi, let's to talk about the population model again. Do you remember in Module 1, the first lesson, we talked about the population model and the Lesson matrix, love coverage matrix. And today, we want to revisit the population model, but use different mathematics tools and the different software tools. And then you're going to learn they always have different ways to skin a cat. So first we're going to talk about the Module3 model. That's the first population model in the record. And then we're going to look at two modified population model. One is called the carrying capacity model. Another one is the computational model. And then we're going to look at a simulation for the stellar. And I will leave the MS Excel simulation as exercise. And then we are going to talk about the Lesson matrix and use stellar to model the same problem. So the Module3 model is really an oldest population model. It is dated back 1798. That's the end of the 18th century. And the population is really simple, but he's the first one to identify such a crisis of population growth. So in this model, we assume the population changes over time. So it's a function of time. Well, you can think about the population of a human being in the world, or a population of a colony, or even the population of some ants, bunnies, doesn't matter. It changes over time. So we focus on the growth rate. We know the growth rate also includes the birth and the death in whatever reason. But this rate is, of course, proportional to the population itself. So, for example, if in a colony, each mother have 4 babies, and then you probably expect that the population will double after 1 generation. As soon as the parents die, 2 die, and then 4 matured as adult. So that case would be 2 intuitively. Well, then we write it into a differential equation. The growth rate is the change of a population over the change of time, and then equals the population. If you count only female, then the population of the mother you can divide by 2, but then you multiply the k, which equals the birth rate per mother minus the death rate per mother. If the PT is the population of the female only, or if assume the female and the male have equal probability, you can talk a whole population, but divide this k by 2. That's all your choice. Anyway, and then you need to know what is the original population. Depends on what you believe. Doesn't matter. You count this as a constant. You know, 2 or 2 million. So this kind of equation, we call it a separable equation. That means you can divide, let me look at one more time, p to the left hand, and then move the k dt to the other hand, and then you do an integration, and in this case you get the logarithm of p equals k dt, and then take an exponential, and then your p equals I need to add the c, right? If you do an integral and then you add the c1, then you can call it c2 e to the k. When you do the integration, you got a t, right? And the kt, what is the c2? c2 is e to the c1. Then you use the initial population, let t equal 0. The initial condition is p0 equals c2 e times 0, which is c2. Then you get your c2 equal p0. The solution will be pretty simple. Population is a exponential function times the initial population. Well, so that's not new. I believe this is not new to you at all. Just like you save some money in the bank, that p0 is the principal you saved, and the k is the compound annual interest rate. And then the money you gain from the compound, the interest, is the same formula. The bottom line is, this is an exponential function, depends on k positive or k negative. If the k positive, you get a exponential growth that may be like that. If the k is negative, you get the so-called decay. We're going down like this. So our population in the world, in the developed country, is like decaying. In the developing poor country, is growing. That's the basic phenomenon. Well, we got an answer anyway, but the next is more important. What do we learn from this solution? What did the solution really give to us in such a function here? Let me highlight this here. Before we jump to any conclusion, let's look at the real world population from 1800 to 2100, about 200 years in the past, 100 years in the future. So this curve gives you 3 different colors. The black color is a backward estimate by all the history facts that end up in 1960. That's right here. Because before 1960, there's no systematic census. And then between 60 to 2000 right now, we have a record of the census. That's a pretty accurate estimate. And after this, we have 3 predictions. One is the red line continue to grow in the same pace. Another one, like the yellow grown, is the moderate growth and started to slow down, but still growing. And the green line, pretty much all like the developed country, like Japan, Belgium, North European, Singapore, also all like this. Even China now start to be like that. So it's all possible. We really don't know. But we certainly know the Mars session model cannot be continued grow like an exponential function. See, according to the solution we have, the P equal P0 e to the kt. If we assume the k is positive, you got this green red line. So if we are right here, we have 8 billion people, and that means if we continue the growth rate as 100 years ago, we probably end up with 800 billion, 8,000 billions. That's all possible according to the mathematics model and the old pattern. But here is the real argument Malthus originally gave. He said, watch out. Look, if the population keep like double, at his time it's not a double, maybe 4 times growth. And you got this red curve, but look at our food supply. Our food supply is really a straight line increasing. The mathematics term for the growth like this, we call it a geometric series. And that line, we call it arithmetic series. The difference is that first, the geometric series keep double. And the arithmetic is you keep add 1. And the 1 is multiply, another one is addition. Of course, you cannot match the speed in some point. So that will be the point Malthus concluded. The human being will be either controlled or wiped out by war, famine, disease, so on and so forth. He called it a regular check. That means correction. Well, of course, nobody liked that. War, famine, disease, it happened again and again. And then they said sooner or later, you're going to reach the point you don't have enough food to supply the population. So that kind of limit, they have a name, is called the carrying capacity of the environment. It's very easy to figure that out. If I put a few rabbits, female and male, in this flow, I prepare a ton of food. Well, then these bunnies were going to reproduce like rabbits. They are rabbits. But the sooner or later, they're going to run out of the food. They cannot reproduce anymore. They're going to die out. That's the same fate to the human population unless we make a wise decision. So the bottom line is, it's not a question whether the Malthus model is right or wrong. It's really he, as the first person, watched the problem, and we need to pay attention. So again, confirm what I told you, mathematics model is not about a number. None of those numbers are right, but it's about insight. The insight is we do have this carrying capacity.